All right. So lecture 4.2, DC motor driving. So there are two common methods of driving DC motors. A, with a digital motor driver, and B, with an analog amplifier. Schematics of both are shown in figure 4.2. So let's look at the digital motor driver setup first. We've got our microcontroller, which in our case is the MyRio, right? But it could be any microcontroller that you've got. That's got microprocessor on board. It's got some input-output capabilities with some pins. We've been, of course, working with the MyRio microcontroller for a few weeks now. And we're going to use PWM from its digital outputs. Okay, so it's got some digital outputs. We'll use a PWM signal, pulse width modulation signal that we just learned about. And we're going to give that PWM signal to the driver. Okay, motor. This is a digital motor driver, and this is well, we're going to talk a little bit about it in a minute, but it's a device that allows us to essentially gate a constant but more powerful DC power source supply. So, of course, a DC power source typically is getting its power from an AC line, but if you're on like a mobile robot and it's coming from a battery, it just comes DC straight from the battery, which is great. But in many applications, it'll come from a DC power supply. These two, I said that we were going to bring the PWM signal from the microcontroller together with a powerful constant signal that comes from a constant but powerful supply, DC power supply. And that's what we do in the motor driver, the digital motor driver. We take the output of that signal, and then these are, of course, I wasn't really showing the leads here, I'm just showing connections. Now I have the plus and the minus leads that go to the motor that come out from the driver. So the driver delivers the gated, powerful DC signal, PWM signal. So that's the digital motor setup. We'll also return to the situation where we use the analog output of the microcontroller going through an analog amplifier, and the output of that amplifier going into the motor. So that's an alternative way of doing it, and I'll talk about the two different methods and how they work, and then comparing them a little bit, talking about applications. So this lecture is about. So digital motor drivers, a microcontroller such as the MyRio or an Arduino can easily produce a PWM signal, which, as we saw in lecture 4.1, can be averaged by a system's dynamics such that varying the duty cycle varies the averaged signal. However, microcontrollers are low power and cannot drive even small DC motors. Therefore, it is common to include a special kind of integrated circuit that uses the microcontroller's low-power PWM signal to gate a high-power DC source signal for delivery to the motor. These are called digital motor drivers. Common setup with a motor driver is shown in figure 4.2a, we just reviewed. They deliver power from a high-power source in accordance with the PWM signal, and they often include many additional features such as being in compact forms, have forward and reverse driving, so you can switch the direction of the motor rotation, protection against reverse voltage, overcurrent, and overheating, and output pins that monitor delivered current and voltage. So a lot of these come with a lot of like nice extras that are not just about delivering power to the motor. It tells you stuff about what's going on in the motor. It protects the circuit from damaging your microcontroller or the power electronics. So really nice. And they come as integrated circuits. and can be, relatively inexpensive. These digital motor drivers are sometimes called Class D or switching amplifiers. Generally, they're inexpensive and quite efficient, around 90% in some cases, which in addition to conserving power, adds the capacity of delivering high power operation or requiring lower heat dissipation, or a Goldilocks mixture thereof. So the idea is that if you're more efficient, so where is all the power going when you're inefficient, typically? Heat, okay? So heat can, first of all, it's waste power. We don't like that. We don't like wasting power. But also heat can damage things, right? So if it heats up too much, you have stuff melt, breaks. It's not good. So we don't want to heat stuff up too much. You have to have all kinds of heat sinks in there, fans blowing things off. But that can limit how much power you can do, right? As a secondary effect, because the heating can damage things. So sometimes heating actually is your power limiting factor if you can't get heat out fast enough. So when you are conserving power and keeping your stuff relatively cool, you can ramp up the power even more, right? Of course, there's going to be a point where you're going to heat up too much, but you can get to a higher power that way. God, No, okay. I just realized I said higher power. Little bells went off in my head. I went to Sunday school, So, okay.
Did you have the hair in Sunday school?
Did I have the hair in Sunday school? No. It wasn't that kind of Sunday school. It just wasn't. I don't know, are there Sunday schools where you can have long hair as a guy?
I went to a private Christian school. I know some guys with hair down here.
Wow. I guess Jesus had long hair. I mean, if we know anything, it's that Jesus had long hair. I think it's clear. Okay, H-bridge circuits. We want to drive DC motors at different effective voltages and different directions. Okay, so don't want to just go up and down with positive voltage. We want to be able to go down and up with negative voltages. So that's where H-bridge circuits come in. An H-bridge circuit allows us to reverse the direction of the PWM signal delivered to the motor. Figure 4.3 is a diagram of the H-bridge circuit. So, it's up here. So, the idea is, the green lines went away. You've got your motor here, and it's got, say, it's plus and minus terminals, say plus and minus, and if you put voltage across that direction, then it rotates in a certain direction. Okay, so in off mode, you've got 4 switches here, so they're often MOSFETs or some sort of transistor that can be operated as switches that are open. So when those are open, you've got a high voltage here and a low voltage here. The diodes are off and current's not flowing, right? If you throw switch 1 and throw switch 4, close them, then current has a path to flow through the motor this direction. Great, and it does not have a path to flow that way because the voltage drop is this direction, so it's not going to go that way. And alternatively, if you wanted to go the other direction, you could apply the same voltage through the other side. So throw switches 3 and 2 instead of 1 and 4, and current will flow this way. So in this one, current flowed that way, and in this one, current flows this way. So it's kind of nifty, right? It's a pretty cool setup. And another thing that can be done here is to use the diodes as a way of mitigating inductive load kickback that can happen. There are many ways of handling that electronically, and a lot of motor driver circuits have ways other than using the diodes to do that. So this isn't typically the way that they're going to be mitigating that, but that is one possible way to deal with it. So yeah, so the motor can go both directions with a signal that only is positive in one direction until it hits that bridge, right? You can't put a negative voltage in VS. You can only put positive voltages, but you can flow that current in one way or the other way. So great. So that's pretty much the digital motor driver way of doing things. So that was figure 4.2a. That's this method. This is a good method. This is how a good number of DC motors out there in operation are operating. Great. Analog amplification. An alternative to digital motor drivers are analog amplifiers, which require a slightly different setup, shown in figure 4.2b. So in this setup, we again have a DC supply that is supplying our power. We again have a microcontroller that's supplying the signal, the control signal, in terms of how much voltage or current should be applied to the motor. And the analog output is being used this time. So our MyRios and most microcontrollers have the ability to put out an analog signal, not at just on or off, so not just logical high, logical low, with a digital signal like we looked at last week, but with a variable voltage from anywhere, in our case, from plus 10 volts to minus 10 volts. And there are increments that are possible along that spectrum. So that's the resolution. The setup requires an analog signal from the microcontroller, which is a digital device, remember. So you're going to be like, I want to put out 4.72642 volts out. And it's going to say, great, I can do something close to that, and it'll put that voltage out. So the microcontroller has to perform a process called digital to analog conversion, which is treated further in lecture 6.1. So in a few weeks we'll get there. We'll talk about how digital to analog conversion works and what its limitations are and all that. But for now, we know that it can produce an analog signal from a digital board, which is great. And resource 12 also talks about that. Many microcontrollers have this functionality and can produce analog signals over ranges such as plus or minus 10 volts. The range of the MyRios CIO channel analog outputs. So channel C's got plus or minus 10. There are a bunch of analog outputs that can do 0 to 5 volts in connectors A and B, I think. But connector C has got the good ones. Plus and minus 10 volts can do. And the resolution's better than those. An amplifier essentially adds power to the microcontroller analog output from an external power source. There are several varieties that can operate as voltage or current controlled voltage or current sources within a range of operation. So you can have a voltage-controlled voltage source, a voltage-controlled current source, a current-controlled voltage source, or a current-controlled current source. I got them all. So we are putting in some small signal that is going to, we typically use voltage to control things. So typically have voltage-controlled voltage sources or voltage-controlled current sources. It's very rare to use current as a control, but it's possible. So we've got these two possibilities. So whatever voltage is being put out by the myRIO analog output, the amplifier is going to take and put out a signal at higher power that is proportional to that. It's either proportional in voltage or proportional in current. Okay. When that range of operation is exceeded, so when you ask for more voltage out than it can provide, or you ask for more current out than it can provide, then it will saturate. Okay, so it can't go beyond a certain amount. So increases in the input don't get reflected in the output. Saturation is, of course, one of several considerations when designing with amplifiers. You might want to go beyond the saturation of some amplifiers, so you need to look at other options. Or if you could do something different about what your needs are in terms of power amplification. So that's kind of that idea. Another thing that happens when you get up to those near those saturation points is that the input-output characteristics tend to become very nonlinear. So, if you put in delta X, some change in the input, you get out some delta Y, and then that works linearly for a while, and then you put in delta X once you're getting pretty high or pretty close to those saturation values, and you don't get out delta Y now. It's just you get out something much smaller than delta Y. So your ability to operate linearly can be important, especially because we will tend to model amplifier dynamics as being linear, and if they're not operating linearly, what we expect them to do is not what they'll do.
So what's the saturation point?
So for us, our amplifier, well, we'll talk about our amplifiers, but I think it's like plus or minus 20 volts for ours. It just depends on the amplifier. And then there's a current too. I think ours is operating at max 4 amps. So nobody dies. No. It's operating at 4 amps in part to be safe. But that's the saturation current that we're setting for it. Actually, it's capable of doing more, but put on some safety measures. So. Great. A comparison between digital motor drivers and analog amplifiers is given in table 4.1. So let's see this comparison. So we're going to compare the digital motor driver setup to the analog amplifier setup and just talk about the considerations here. So first off, cost, this is the first one we're going to look at. Digital motor driver is less expensive than the analog amplifier. Often significantly so, which pretty much means that if you can get away with a digital motor driver, that's the way to go. So if you can get away with the performance stuff around it, then you want it because it's cheaper. Okay? So the economy of it comes into play here. One issue with these digital motor drivers, or sometimes called switched supplies, is that you inject all of this, this pulse waveform at a relatively high frequency, and any sort of pulsed waveform is going to have really high frequency components in it. So pretty much all the electronics around you through electromagnetic interference or ground loops or various manners. Voltages are great at finding their way into other stuff nearby, sometimes through wiring problems and sometimes through literally the air, sometimes through proximity. You can, if you start to include switched supplies, digital motor drivers into your system, you're going to have lots of high frequency stuff showing up in all the measurements that you're taking. So that can include like measurements for what the motor's doing. It can include any measurements that you may be interested in. Probably that noise is going to get in. Of course, you can filter it out, but then you have all the issues with filtering, the costs associated with that. So it's not ideal if you care about measuring things precisely. It can be an issue. Analog amplifiers don't use those high frequency switched signals, so we don't have to worry about it. Audible noise. So actually, loud is what I was trying to say there. Loud. Digital motor drivers are loud. You can actually hear them when they're on, and you guys will be able to hear them in the lab. I want us to use, we'll talk about the stuff in the lab. I want you guys to use it so you can hear the whine. It's really fun. It depends on the frequencies that you're using and the mechanical structure around. So it'll actually be making the structure sing a little bit. So that's fun. Analog amplifiers don't have that. So low signal fidelity. What we mean by this is that when you want to go from, say, a small negative voltage like negative 0.1 volts to a small positive voltage like 0.1 volts, you're going through 0 volts there, and you're getting to the point where your PWM duty cycle gets really small. And it's tough to get good resolution. I mean, the higher frequency you're working, the better. But it's tough to get really good resolution when you get down to near 0 volts, when you get very low duty cycle. So what you'll see is, if you have this issue, you'll have a really hard time stopping at a precise small value of anything. It'll kind of float back and forth, and that can cause your motor to move back and forth potentially, or there can be other issues that arise with the low signal fidelity. So it's good for an analog amplifier. It doesn't have this issue. So digital motor drivers, not great for that. Therefore, high precision control isn't very good. So if you want to do very, very tight high precision control where a small difference matters to you, it's hard to do a very small amount with one of these digital motor drivers, whereas with an analog amplifier it's better. However, so you might think, wow, the only thing going for the digital motor driver is that it's cheap. But they're actually quite a bit more efficient than analog amplifiers. So the efficiency is like 90% about in common operating conditions, whereas for an analog amplifier, because we have these transistors on all the time, they're going to be sucking power faster. So they're not as efficient. And therefore they heat up, which means that high efficiency stuff has low heat generation and can be high powered, whereas inefficient stuff has high heat generation and has to remain at relatively low power. So that's the sort of trade-off there. They can both be used for brushed and brushless DC motors, so that's not really an issue there. H-bridge is required for a digital motor driver. Analog amplifiers are usually built to be plus and minus, so you don't need to put in an additional H-bridge circuit. So that's sort of comparison of the two. Okay, finally, we'll talk about what's in the lab. So the embedded computing lab has both digital motor drivers and linear analog amplifiers, both of which are commercially available. So the digital motor drivers are from Pololu. They come on connectorized circuit boards. The drivers are on these Pololu boards. They're called carrier boards. So the drivers are actually a common automobile motor driver. So they might show up in like rolling up your window, rolling down your window in the car, or moving your seat forward or backwards. So they're commonly used for that type of application. They would be on some printed circuit board that's not this carrier board that comes from Pololu. So it's a chip. It's an integrated circuit, the driver itself, and we buy it connectorized for doing prototyping type stuff so that you can just plug stuff into it. If it's going to go on a car, though, it's going to be on a motherboard of some sort that's got lots of chips on it and other circuitry on it. So when you're doing prototyping, though, it's nice to get them as on a carrier board so that you can just essentially connect stuff up to it and try it out. So yeah.
So you can just drive the motor without a microcontroller?
No, you need the microcontroller because you need to have the microcontroller PWM signal to tell the driver what to do. So the driver is just saying, I'm a little gate and tell me when to open. Like it's essentially doing that. So it's like the gate that like lets through a lot of power and closes the gate, and it pays attention to somebody, the microcontroller, telling it open, close, open, close. Yeah. So it's essentially Hodor. That was a reference that I thought a few of you would get. Okay. Great. So this is that's the one that's in the lab. We're mostly going to be using this analog amplifier instead, but I want to try to work in some digital amplifier stuff later on. So this one's actually kind of both. So there's a Copley Controls 412 voltage controlled current source, which is also called a transconductance amplifier in the lab, and they're actually switched amplifiers down at the heart of them. So internally, they're actually quite efficient, but they function on their outputs. They like spoof being an analog amplifier. So they function as analog amplifiers. So if you put in this small voltage to it, it'll put out a large current that's proportional to the voltage. It doesn't need a PWM signal. It needs an analog input. But internally, it's kind of giving you some of the advantages of the switch supply, but it will come with some of those disadvantages as well. So it's kind of an in-between situation. This is a standard type of motor amplifier found in industrial settings. So Copley Controls does a lot of like automation type stuff that you would find in manufacturing environments and whatnot. The device manual can be found here for the amplifier settings used in the lab. So there are a whole bunch of settings you can use. Some of them are like limiting the current and all that. So you have to set different resistor levels that you connect to it and all that. So for all those settings, see resource 10, which is at the end of this chapter. Okay. Any questions on driving motors? Ooh, a question.
Can you do pulse width modulation on like a stepper motor?
Ooh. Stepper motors are just a very weird type of motor. They're almost a special case. I don't know. I've never seen anybody try putting in PWM because the operating principle of stepper motor is that you put in a pulse with enough power behind it, and it will turn a certain increment. So pulse width modulation at that point, I don't think that you can do multiple pulses to get the average power over a certain time interval. I've not seen that. Maybe that's possible, but to my knowledge, it's one pulse for one step is how they tend to operate.
I mean, I'm just wondering how else would you control power to a motor like that?
A stepper?
Yeah.
Well, it's tough to know what's going to happen if you don't have enough torque. So if you send the pulse and it doesn't turn,
It slips back.
yeah, so if you can't make it over to the next slot, then it's just going to stay where it is, or it'll try to move and get stuck. So in those cases, this is part of why. So if you try to do position control with steppers, you still often need to measure what's actually happening, because you'll send pulses and they won't step every time. They step most of the time, but they don't step every time. And then if you run into a situation where it's totally like there's too much torque, can't turn, then you're just sending pulses and it's just heating up. But that's an issue with all motors. So yeah, pulse width modulation, although it looks kind of similar to what you do with steppers, really you want there to be the full power necessary at each pulse that you send to the stepper so that you do get the motion. Yeah. Okay. I think that's all I've got for that.